Okay, so we begin section 3.3. The section is entitled Logarithmic Functions. And in the previous section, 3.2, we studied what were called inverse functions. And we saw that basically an inverse function exists when a function is 1-to-1 or passes the horizontal line test, meaning every horizontal line can only intersect the graph at most one time. Excuse me. And this came after studying exponential functions. And we're going to see that the reason for the detour to study inverse functions is because logarithmic functions and exponential functions turn out to be inverses of each other. And for this lesson, just recall that given a 1-to-1 function, the way that you would find the inverse function, the basic idea is that you're really just swapping inputs and outputs. Okay. So first of all, before we actually talk about logarithmic functions, I want to talk about logarithms, and and I'll explain this in just a moment, where this comes from. But okay, many of you maybe have seen this before. You may have, you may not. But if I want to find the logarithm, base b of a, so b here is what is called the base. I'm going to think of, let me pick a good color. I'm going to think of a as the input. Okay, so log base b, let me box this up right here. Log base b is notation for a function, and a is the input. You might want to think of it this way, log base b of a. That might help you think of function notation. But what I'm going to say here is that the output, or the value of this logarithm, if it is c, this happens if and only if, now this is where this comes from. If you think of a as the input and c as the output of the logarithm, log base b of a equaling c. Now, if you think about swapping inputs and outputs, log base b is really the inverse of the exponential base b. So log base b of a equals c precisely when you raise the base b to the c power, you get the number a back. Okay. And I'll talk about this more precisely again later. This fact will be used over and over again. So log base b of a equals c whenever the base b raised to the c power equals a. And basically, if I come down here, right, if I think about the exponential function base b, c now becomes the input, and a now becomes the output. Okay. So sorry, I know I'm all over the place. Clean this up a little bit later. If you want to keep these two ideas separate, you can. But the whole idea of a logarithm base b is that it's the inverse of the exponential base b. And really, this whole converting between logarithm to an exponential to evaluate logarithms is just coming from inverse functions. So for instance, if I come down here and I want to find the value of, oops, let me get rid of this. Give me a moment. Okay, so if I want to do example 1, This is just an example of computing logarithms before we even talk about functions. Okay, so as usual, my video paused itself, which is frustrating. So, again, let me explain this one more time. To compute a logarithm, we use the fact that log base b equals c whenever or if and only if the base on the log b raised to the c power equals a. So for example 1, let's say log base 3 of 27, let's say that's equal to x. Okay, so we're going to find the value of x. Okay, a logarithm is equal to some number. Okay, what that means, if you convert this to an exponential now, is the base 3 raised to the x power has to equal 27. And from here, okay, the only thing that you can raise 3 to, so the only power on 3 that gives you 27 would be 3. I guess you can come back up here. Right, 27 is 3 cubed. And, ooh, shoot. That is not what I wanted. Sorry, I clicked the wrong button there. So I was saying 3 to the x equaled 27, and 27 is 3 cubed. And this power has to equal this power if the bases are going to be the same. So x is equal to 3. So that implies log base 3 of 27 is equal to 3. Okay. Again, the idea, right, 3 is the base, and the value of the logarithm is the power, and the 27 is the base raised to the 3 power. Okay. So log base 3 of 27 equals 3. Okay. So another example. Okay, so for the next example, we're going to do part B, which is trying to find log base B of, log base 10 of 100,000. Okay, so I want to compute this. And, again, the process is to, okay, log base 10 of 100,000 equals some number, let's call it x. And doing the conversion, this means the base 10 raised to the x power has to equal the input 100,000. Okay? And if you like, you're basically just, whenever you're doing a logarithm, you're just saying what power does the base have to be raised to give you this input value. And if you like, you can write the value of 100,000 on the right as 10 to the... Now, basically, any number that's first digit is 1 followed by a number of zeros, it's always going to be 10 to the number of zeros as the power. So 100,000 is really 10 to the 5th. And the only way that 10 to the x can equal 10 to the 5th, you can... I don't like this idea, but you can kind of think of canceling off the bases, but the powers have to be identical. This is really because exponential base 10 is a one-to-one function. Okay, so if I take 10 to the x and it equals 10 to the 5th, the inputs x and 5 have to be equal. So x is equal to 5, which means log base 10 of 100,000 equals positive 5. Okay? So that's that one. And moving on to the next one. Okay, so now I want to find log base 2 of 1/16. And again, the process is I'm just going to say that this number for now is x. And now I'm going to convert. You're basically saying, okay, 2 to what power equals 1/16? Okay, ultimately I know the answer. But the process would be setting this equal to some number x. That means 2 to the x has to equal 1/16. This time you're trying to get the right side written as a power of 2. The 16 in the denominator is 2 to the 4th. And then you can use a rule of exponents. 1 over 2 to the 4th is 2 to the minus 4. And that means that x has to be negative 4. And hence log base 2 of 1/16 is negative 4. Okay, now again, this is because 2 to the negative 4 is really 1/16. That's a sloppy 1/16. Okay, so I could have really said that at the beginning. What power do I have to raise 2 to get the 1/16? And 2 to the negative 4 equals 1/16. So that's why the value of the logarithm is negative 4. Okay, so if you get good at these, you can basically write down the answer. So if you know this time, if you know that 2 to the minus 4 equals 1/16, you're done right away. Okay, example 2. Find the value of each logarithm, and I'm going to do this rather quickly. Log base b of 1. Now, for this first one here, you are basically saying, what if the base is b, and I'm inputting 1, I'm saying, what power do I have to raise the base b to get 1? In this case, sorry, let me switch back to black. In this case, I'd get 0, and this is because b to the 0 is equal to 1. So the base raised to the 0 power equals 1, so that's why the value of the logarithm is 0. Okay, b, log base b of b. So I'm saying, what power do I have to raise the base b to get the number b back? And the only power you can raise b to get back b is 1. And again, this is because b to the first power equals b. Okay, nothing surprising there. Okay, log base b of b to the p. So if the base on the log, okay, this is actually going to be an interesting property. We're going to see this probably in the next section. But if I take log base b, followed by an exponential expression base b with power p, this is kind of silly. The answer, the value of this logarithm would be p, because what do you have to raise the base b to get b to the p? Well, the power would have to be p. So this is because b to the p, okay, so the base raised to the p power equals the input b to the p. So this one's kind of silly. And finally the last one down here, log base b squared. So if the base is b squared and the input is b to the 8th, this time you'll see that log base b squared of b to the 8th equals 4. And this is because, well, b squared to the 4th power. So if you take the base raised to the 4 power, when you raise a power to a power, you multiply exponents and you get the input b to the 8th. Sorry about my parentheses here. Could have probably done a better job writing those. There we go. Okay, so log base b squared of b to the 8th equals 4 because the base raised to the 4th power gives you back the input b to the 8th. Okay, so now that we've computed some logarithms and we understand the basic connection between, hopefully you see the connection between logarithmics, like computing logarithms and exponentials. So now for the definition. A logarithmic function for any base b greater than 0, so just like an exponential, we only care about positive bases, and the base b is not equal to 1. The logarithmic function base b, okay, denoted log base b of y, sorry, I needed to switch to pen mode, so denoted log base b of y is the inverse of the exponential function. Okay, f of x equals b to the x. So here's the basic idea, I guess. When you look at this expression right here, sorry, let me erase that and rewrite. When you look at this expression right here, b to the x equals y. In this case, x is the input of the exponential and y is the output. Since the two functions are related by being inverses, when you convert to logarithmic notation, notice that y has now become the input on log base b. So log base b is notation for the function. Okay, and again, look over here on the left. So the comparison here is that on the left you have the exponential function base b, input x, output y. On the right you have the function log base b with input y and output x. Okay, so that's the relationship. The function logarithm base b is the inverse of the exponential base b. Okay, and the inverse of the natural exponential function y equals e to the x, so if the base on the exponential is e, that's called the natural exponential function. The natural logarithmic function is denoted by ln y, and I'll write this down if you look in the bottom left corner for just a minute. This notation ln just stands for log base e, and if you look over here on the right, the inverse of the basic exponential function 10 to the x, some people call this the common logarithm. This shows up commonly, it shows up in chemistry applications. pH is based on a base 10 system for this. That's why that's called the common logarithmic function. And you just simply drop the base and write LOGY. And again, if I just write log, I'm talking about log base 10. Now, these equal signs are kind of misleading. I shouldn't be writing that. That's bad math, teacher. I should really be saying log of x is the same as log base 10 of x, and natural log of x is the same as log base e of x. Okay. Now, if you look at the functions, you have f of x, so now look at the bottom right here, if you focus on this box. The function f of x equals b to the x, that is the exponential function base b, has domain all real numbers in range 0 to infinity. The inverse function, f inverse of y, would be log base b of y. So again, notice that you use the same base in both. There's exponential base b and there's logarithm base b. Notice that the domains in range have swapped because they are inverse functions. So we learned in section 3.2 that when you convert from a function to its inverse, the domain becomes the range and the range becomes the domain and vice versa. Okay, so we've talked a little bit about the definition of a logarithmic function. Let's talk about the graph of a logarithmic function. Okay, so suppose I want to sketch a graph of the function f of x equals log base 1/2 of x. Now, first thing to notice, probably, or to think of, is that this is the, sorry my cat is being insane right now. Okay, so if I'm trying to graph log base 1/2 of x, okay, the first thing to notice is that log base 1/2 of x is the inverse of f of x equals 1/2 to the x power. Okay, so again, the base on the log is 1/2, so the inverse would be the exponential with base 1/2. Now, in terms of graphing, what I can do is I can simply think of plotting some points into my exponential function. Sorry, cat keeps bumping into my iPad, making writing difficult. There we go. Okay, so if I want to graph log base 1/2 of x, what I can do is I can first plot points or think about points on the graph of 1/2 to the x. And I'm just going to use the coordinates, or the x coordinates, -1, 0, and 1. 1/2 to the -1 power is the reciprocal +2. When you plug 0, 1/2 to the 0 power is 1. And 1/2 to the 1 first power is 1/2. So now, if you make a table for log base 1/2 of x, the only thing that's going to happen here is that the x and y coordinates are going to be swapped. So any x value becomes the y value, and any y value becomes an x value. Okay, now I can plot these 3 points, so I could go 2 to the right and 1 down. At this point, I could go 1 to the right and 0 units up or down. And then I can go 1/2 unit to the right and up 1 unit. That would be about right there. And I maybe should have talked about this a little bit earlier, but where the x-axis is a horizontal asymptote for the exponential functions, the y-axis is always a vertical asymptote for an exponential function. So the graph of this looks something like this. So the vertical line x equals 0 is a vertical asymptote. In the case here, the base is 1/2. That's between 0 and 1. And the logarithmic function decreases from left to right, and it does turn out that this does go down and to the right forever, because again, the range of a logarithmic function is always all real numbers, and that's because the domain of an exponential function is all real numbers. Okay. So one thing I should have maybe talked about real quick before I move to the next example. Example 4, I'm just going to do a transformation of log base 1/2. So we're going to look at graphing a transformation of a logarithmic function. But before I do that, let me real quick talk about the shapes of graphs of logarithmic functions. I probably should have done that before this example. Okay, so if I just look at the function, if I just think about the function, say, okay, f of x is log base b of x, and there's going to be 2 cases for the graph. Just like an exponential function, the base can be between 0 and 1, or the base can be greater than 1. Okay, so I'm just going to draw a set of coordinate axes. Here's the x-axis, here's the y-axis. When the base is between 0 and 1, you always get a decreasing exponential. This is the graph of log base b of x. And let me switch colors. That's supposed to be the inverse of the exponential function base b. And an exponential function base b looks like this. So the blue graph is b to the x. And Again, if I think about the line y equals x, you should be able to hopefully convince yourself that those functions are reflections of each other over that line y equals x. Okay, so I can also think of the case where the base is greater than 1. Here's a set of coordinate axes. And in the case that the base is greater than 1, the exponential function will actually be increasing, and the y-axis is still a vertical asymptote. So this is the graph of, see, I'm running out of room here. That's the graph of log base b of x, and that's supposed to be the inverse of an increasing exponential function. So this is probably the graph of b to the x. And again, since there, oops, that was really not a good example of a line y equals x. Let me see if I can do this right. There we go. So that's the line y equals x. And you can see the black graph is log base b. The green graph is the function b to the x. And they're supposed to be reflections of each other over the line y equals x. Okay. So I didn't mention that before. And again, the fact that the x-axis is a horizontal asymptote for the exponential function base b, if you think about swapping x and y coordinates, I think you can hopefully convince yourself that that's why the y-axis becomes a vertical asymptote for the logarithmic function. Okay, so let's graph a transformation. Alright, so now I'm going to first of all find the domain and range of the function log base 1/2 of 2x minus 4 and then sketch a graph. Now notice that I'm still doing log base 1/2. That's the original function that we just graphed in example 3. So this is supposed to be a transformation of that, of the function log base 1/2 of x. Now, the first thing I want you to notice, or what I'm going to do here, is I'm going to factor the 2 out of the 2x minus 4. And if you think about transformations, that means that a is going to be 2 and b is also going to be 2. So you're going to get we're going to be doing a horizontal compression by a factor of 1/2. And then we are also going to be doing a shift to the right 2 units. Now, just like with transformations of exponential functions, the vertical shift tells you, where the new horizontal asymptote is going to be. This time, the horizontal shift tells you where the vertical asymptote is going to be. So since b is positive 2, and for an untransformed logarithm, the y-axis is the vertical asymptote. With a shift to the right 2 units, this time your vertical asymptote is going to be the line x equals 2. Okay? Now, let me actually make some room for myself. I'm going to write this up above for a second. Let me rewrite this. Okay, a is 2, b is, so a equals 2, b equals 2. Now, if you look at the previous example, we got 3 points that were on the graph of log base 1/2 of x. We had when x was 2, the log was -1. When x was 1, the value was 0, and when x was 1/2, the value of the log was 1. And now, oh, I should have done this in the other direction. Let me remake my table. So actually I need room to modify the x coordinates because there's really there's only horizontal transformations and those affect the x coordinates. So let me actually use x and y. So my values were when x was 2, y was -1. When x was 1, log base 1/2 is 0. So remember this is log base 1/2 of x. And when x was 1/2, this was when y was 1. Okay. Now, first, you always do the horizontal stretching or compressing first. Now, since a is 2, we're going to multiply the x coordinates by 1/2. So I get 1, 1/2, and 1/4. And then since b is 2, we're going to shift to the right 2 units. So I'm actually going to be adding 2 to all the x coordinates and get 3. 2.5, and I'm going to use decimals. 1/4 plus 2 is 2.25. These are now my x coordinates. Those are still my y coordinates. So I'm going to go 3 units to the right. 1, 2, 3, and I'm going to go down 1. There's a point on the graph. I'm going to go 2.5 units to the right and go, well, I'm going to be on the x-axis. This is going to be hard for me to do. And then I'm going to go 2.25 units to the right, and I'm going to technically be at +1. And this is just a rough sketch. There is the graph of log base 1/2 of 2 times x minus 2. Now I graphed this first. There's several ways to get the domain and range. You can probably just graph it and then use the graph to get the domain and range. I'm going to erase my little table here for a second. And looking at the graph, hopefully you can see the domain. Since there's been a shift right 2 units, the domain is 2 to infinity. And the range of a regular logarithmic function is all real numbers. No amount of transformations change the range. So any transformation of a logarithmic function still has range -infinity to infinity, or all real numbers. In this case, the domain of 0 to infinity has just been shifted to the right 2 units. Okay. Other questions will ask you to find x-intercepts and y-intercepts. I can certainly show people how to do that in class, or you can certainly read examples in the textbook. So another I guess another skill you can have is if you want to graph a log. Well, if you want to graph any function, you can always try and find the x-intercept and the y-intercept and plot those points as well. Now notice this function didn't have a y-intercept because you never crossed the y-axis. You did have an x-intercept of 2.5. Some of this we actually don't know how to do as of yet. I guess we could do this by hand. Maybe I'll show that to you real quick. Why not? Okay, so say I wanted to find... Okay, I'm not sure if you heard this. Every once in a while my video ends up being paused and I forget to push play. But another way to, you could see that this function had no y-intercept and it had one x-intercept. And I guess some of the questions on the homework might ask you to graph a transformation of a logarithmic function, and one thing you can do is you can always find the x-intercept and the y-intercept. So first of all, if I wanted to find the x-intercept, that is sloppy. Let me retype that real quick. Okay, the x-intercept happens when y is equal to 0. So what you would do is you would set the function log base 1/2 of 2x minus 4 equal to 0. Now this is also going to be, essentially I'm showing you how to solve logarithmic equations right now. We're going to do this in its full extent probably in section 3.5, but I don't think it hurts to do this right now. Now, remember we said log base b of any number equals c. What that means is if you take the base 1/2, set it equal to the value of the logarithm, you have to get 2x minus 4. So you get the input back. On the left, 1/2 to the 0, or anything to the 0, is 1. And you get 2x minus 4. You come up here. If I add 4 to both sides, you're going to get 2x equals 5. And dividing both sides by 2, you get x equals 5/2, or in other words, x equals 2.5, which is exactly where the graph crossed the x-axis. Okay, so that's one thing you can always do. If you want to graph a logarithmic function, you can try and find x-intercepts, which is setting the function equal to 0. And then you can also try to find a y-intercept. Let me show you what happens if you try to actually find the y-intercept in this problem. Okay, so a y-intercept occurs when x is equal to 0. Okay, so what happens when you do f of 0? This is log base 1/2 of 2 times 0 minus 4. Okay, this is equal to log base 1/2 of negative 4, which does not exist because the domain of a logarithm is 0 to infinity, right? The input must be positive, okay, or the function does not exist. Okay, so there is no y-intercept, but we saw there was an x-intercept. Okay, so next thing, or last thing we need to do is talk about inverse properties for exponential and logarithmic functions. Okay. So, for any base b greater than 0, and again the base always has to be positive and it cannot equal positive 1. The following inverse properties hold for f of x equals b to the x, and f inverse of y equals log base b of y. Okay, so if you look over here, I want you to look at both these expressions right here, and all this is really saying is if y equals f of x, or if xy is on the graph of f, then x equals f inverse of y, meaning y comma x is on the graph of the inverse. So we saw this before in the previous section that when you convert a function to its inverse, if you're given the graph of a function and I want to graph an inverse function, then what I want to do is I want to basically just swap the x and the y coordinates. So x becomes the output and y becomes the input. So the first thing I have right underneath this boxed what I just boxed right here, is in the world of exponential and logarithmic functions, saying b to the x equals y, that's saying x is the input, y is the output. That's equivalent to saying that x equals log base b of y. So this is converting to the inverse function. Notice now that x is the output and y is the input. Right below that, saying b to the 0 equals 1 is the same thing as saying log base b of 1 equals 0. And finally, b to the first power equals b. That's equivalent to saying log base b of b equals 1. I think we essentially did this in one of the previous examples, so we've already somewhat hinted at this. And furthermore, as long as y is greater than 0 and x is any real number, this little table at the bottom, you saw this in section 3 too. If you compose a function with its inverse, you always just get the input back. So on the left, f inverse of y would be the log base b of y. Okay, and that becomes the power. F is b to the x. So again, f of x is b to the x. F inverse of y is log base b of y. And this expression right here, f of f inverse of y, is just basically saying plug log into the exponent on base b. So when you do b to the power of log base b of y, you get y back. Similarly, e to the natural log of y equals y. That's because, again, ln of y is log base e of y. And 10 to the log of y equals y, and that's because log of y equals log base 10 of y. Okay, and then the same thing on the left. If I do log base b followed by the exponential b to the x, that's composing an inverse function with the original function. So if I do b to the x and I undo it or follow it with log base b, you just get the power back. And similarly, natural log of e to the x is x, or log base 10 of 10 to the x equals x. Okay, so let's take a look at an example. Okay, so I'm going to simplify each of the following expressions using inverse properties. So this first one, 5 halves minus log base 3 of root 27. I'm basically going to leave the 5 halves untouched, and I'm going to subtract log base 3. But I'm going to rewrite this in a different way. First of all, 27 is 3 cubed, and the square root is the same as a 1/2 power. Okay, and then when you raise a power to a power, you multiply. Log base 3, so the 3 cubed to the 1/2 would become a 3 to the 3/2 power. This now becomes 5 halves minus. Now, if I do log base 3 followed by exponential base 3, I just get the power of 3 halves back. 5 halves minus 3 halves is positive 1. So that expression just becomes positive 1. Okay, next problem. Part B. Here I'm going to use a property of exponentials before I simplify this with a log. Okay. Now, log base, again, there's a secret base of 10. When you see this, there is secretly a base of 10 down here. this equals log of. Now, when you multiply things of the same base, you add their exponents. 2 plus x plus 2 is x plus 4. And again, because there's secretly a base down here of 10, log base 10 followed by log base 10 followed by exponential base 10 would just leave you with the power of x plus 4. And then finally, last part, if I'm doing e to the x times natural log of 4, what I'm going to do first here is I'm going to break this up as e to the natural log of 4 to the x power. Again, when you raise a power to a power, you multiply. Okay, so I can go back to what I started with, because natural log of 4 times x is x ln 4. Now, remember, ln 4 is really log base e of 4. Okay, that's what's sitting right up here. So when I do base e and raise it to log base e, you can think of it as these two canceling each other out, and inside the parentheses you're just left with 4, and you still have the x power on the outside. So e to the x ln 4 is 4 to the x. This is going to come up later. I'll probably actually be using this in the next problem. Okay, so last example. Example 6, so if I take two functions, f of x is e to the x and g of x equals 3 to the x, find a value of capital A so that g of x equals f of ax. So what you're going to do is you're basically, okay, the left hand side, g of x is 3 to the x, and then using the definition of f of ax would be e to the a times x. Okay, and this is now saying that 3 to the x is the same as e to the a to the x power. And the only way that this can be true, so this is supposed to be true for all x, the only way this can happen is if the base 3 equals the base e to the a, and then now the conversion, if you convert this back into log of form, the power a has to be, so think about that. A was once the input, now it's the output, and base e exponential is the same as base e logarithm, that's natural log, and a would have to be natural log of 3. Okay. Now, finally, part B. Again, g of x is 3 to the x, f of x is e to the x, and we just saw that g of x is equal to f of ax, where a equals ln 3. So I'm supposed to describe how the graph of f is transformed to be identical to the graph of g, and f is transformed by this factor a. This is the horizontal scaling factor. Okay, so that tells me how much, whatever, depending on the value of capital A, there's times where it's going to tell you to horizontally compress the function f, the original function, or there's times where it's going to tell you it's a horizontal expansion. Okay, so if a is equal to natural log of 3, let me make some space. I can already tell I'm going to run out of room. But notice, so you can plug this in on your calculator. Natural log of 3 is actually greater than positive 1. So this means that g is obtained from f by a horizontal. Now when a is greater than 1, it's actually a horizontal compression by a factor of 1 over a, which is natural log of 3. Sorry for the sloppy handwriting. Sometimes writing with this stylus pen is difficult. So g is obtained from f by a horizontal compression by a factor of 1 over ln 3. Okay, so again, in the case where a is greater than 1, since a was natural log of 3, there's a horizontal compression by a factor of 1 over ln 3. One comment I should make, this problem seems to indicate that basically any exponential function is really just a transformation of any it's a transformation of any exponential function you could think of. Now, f of x equals e to the x, that's your natural exponential function. And 3 to the x, 4 to the x, 5 to the x, 1/2 to the x. Any exponential function you could think of can always be thought of as a transformation of the natural exponential function. Thanks for watching the video. Make sure to work on the homework. Come to class with questions. The homework is going to be posted right now after I post this video, after I convert it to YouTube. So again, thanks for watching. I'll see everybody in class. Take care for now.